This is FlippedHarber for Precalculus. In this video we'll talk about section 2.2, more about functions. Our topics for this lesson are many, but we'll talk about the big ones right now. The average rate of change, the secant line, increasing and decreasing functions, even and odd functions, symmetry, and then a whole list of functions that the text refers to as a library of functions, and then finally piecewise functions. The objectives for the lesson are to find the average rate of change of a function, determine whether a function is increasing or decreasing, determine even or odd functions from a graph, identify even or odd functions from an equation, graph certain important functions, and graph piecewise defined functions. The outline for the video will start by finding the average rate of change. We'll move into secant lines, and then talk about increasing and decreasing functions, even and odd functions, both graphically and algebraically. We'll talk very briefly about this library of functions and where you find it in the text, and then we'll end by taking a look at piecewise functions. Finding the average rate of change is really basically a slope calculation. The average rate of change just takes 2 points on a curve and finds the slope between them. Now, what's going to be different this time is we're finding the slope for curves, not just the slope for a straight line, but a slope that actually talks about or describes a curve. Now, curves have changing slope. So if we take a look at some pictures from the text, we see a nice set of data that creates a nice smooth curve, probably quadratic, and they've drawn in an average rate of change at the beginning of the curve and an average rate of change at the end of the data. And as you can see, it starts out with a very low positive slope and it ends with a much higher positive slope. So you're going to have to get used to the idea of the slope changing. Now that's pretty unusual because in straight lines that slope doesn't change, but now we're talking about curves. Now it's possible to talk about the average rate of change between a generic point, x comma y, and a very specific point on the graph. We do that with this equation, which is still a slope equation. It's still a change in y over change in x, but our change in y takes our function with x's and subtracts from it a specific y value, f of c. The change in x on the bottom, again, takes a generic value, x, the variable, minus a very specific number. So let's find the average rate of change between 1 and x for the function f of x equals 3x squared minus 2x. Now we're going to use this equation, so go ahead and write it down. Now our function 3x squared minus 2x, we're going to find the average rate of change by plugging 1 in for c. So I've gone ahead and done that. So we're finding f of x minus f of 1, all divided by x minus 1. Now before we get started, it's important to talk about the fact that once we're all done, we're going to end up with an expression that we cannot plug 1 into. Because it's a slope, because it's a fraction, if we plugged 1 into this, we'd be trying to divide by 0. You're just not ready for that. You want to learn how to divide by 0? Stick around, we'll talk about it in calculus. Now, if we take f of x, that is 3x squared minus 2x, and then subtract from that f of 1, that means we're plugging 1 into the function, all divided by x minus 1. F of 1 is actually equal to 1, so we get a nice quadratic trinomial, all divided by x minus 1. Now this is all well and good. You've got to show a little bit of faith here. We will be able to cancel things. Sometimes the work to cancel it is complicated. Sometimes, like now, it's not that bad. In order to cancel some things, all we need to do here is factor the top. And as you can see, x minus 1 will cancel out. So we go ahead and do that, and we get 3x plus 1. So this algebraic expression is the average rate of change on a curve between 1 and any value x we want. So if we wanted to find the average rate of change from 1 to 4, we'd plug 4 into that expression. If we wanted to find the average rate of change on this curve between 1 and negative 5, we would plug in negative 5 for x. Now again, It's not appropriate to plug in 1 itself, because way back up top before we canceled, if we plugged in 1, we'd be trying to divide by 0. So whatever you do, don't plug in the actual number that you use to find this average rate of change. Alright, let's move along. A secant line is pretty much just a straight line that goes through a curve in 2 spots. Now, to tie it with what we just talked about, the book talks about secant lines going through that generic point x comma y and a very specific point c and then the y value for that. But it's really just a straight line that goes through the curve at 2 points. Now, the slope of this secant line is equal to the average rate of change that we just found. It's just a slope, change in y over change in x. Now, increasing or decreasing functions. If a function is increasing, it means it has a positive slope. So what we're talking about increasing here is the y values. As you move across the graph to the right, the y values increase. Decreasing functions do the exact opposite. They have a negative slope. If they're not increasing and they're not decreasing, then that's what we call a constant function. It has a 0 slope. It's just a fancy way of describing a horizontal line. Let's take a look at a few graphs here. The first graph on the left is an increasing function. The slope in that interval is always positive. Each y value is higher than the previous one. The second graph is a decreasing function. It always has a negative slope. Each y value is lower than the previous. And the last one is a horizontal line. It's a constant function. The y values are the same all the way across. Now let's talk about even and odd functions. An even function is a function that's symmetric over the y-axis. To put that algebraically, we say that f of negative x, that is when we plug a negative into the function, we get out the exact same thing, f of x, as if we had plugged in a positive. If it's an odd function, it's symmetric over the origin, and what happens with that negative is it ends up out in front, and f of negative x is equal to the negative of f of x. So we're going to look at this both graphically and algebraically. Let's start with the graphs. Our first function here is even. It's pretty easy to spot that it's symmetric over the y-axis. For every xy value on the right side, there's a matching negative xy value on the left side. The third graph, the one that's all the way over there on the left, is actually an odd function. For every point in the first quadrant, xy, there's a point just like it, negative x, negative y. So that's the definition of being symmetric over the origin. That is an odd function. Now the one right in the middle is not even or odd. It's actually neither. It does have some symmetry somehow. It does kind of look similar left to right, but it's not symmetric over the y-axis. It's definitely not symmetric over the origin. So it's not even or odd. Now let's talk about determining whether a function is even or odd algebraically. Now this all revolves around f of negative x. So if I go ahead and plug in f of negative x, I'm going to test for evenness. Is it even or not? So f of negative x means that that negative gets plugged in there and it gets squared. So since that negative goes away, f of negative x looks exactly like the original function. So yes, it is an even function. If I check negative f of x, I get a negative in front of the 2x squared and the 5 turns positive. So negative f of x does not look like f of negative x. So this function is even, but it's not odd. Okay? Now there's no golden rule that I can tell you that if it's even, it's not odd, because there are functions that are both even and odd. Maybe they're rarer, but I can't say a rule that if it's even, it's not odd. Okay, so in the book they have this collection of functions that they refer to as a library of functions. These are all functions that you're very familiar with, except for maybe that last one, the greatest integer function. There's graphs for all of these in your textbook between pages 129 and 131. So take a look at it. Make sure that you could identify which graph goes with which function. That's really the important thing here, is being able to match up the graph with its function. Again, the only one you might not be familiar with is that greatest integer function. Okay, so let's spend our time talking about piecewise functions. A piecewise function is a function that has a different rule based on the x value that you're going to plug in. These different rules come in the form of different equations. So it's like a hodgepodge of 2 or 3 or 4 or more equations all crammed together, and you follow a specific equation based on what x value you're working with, based on where you're at in the domain. Now, some important things to remember. We can't have more than one rule for each x value, which means that we can't have any of these rules overlap even by the tiniest bit. Pay attention to the beginning and ending values for each rule. Now, I want to point out that our first rule stops at 0, does not include 0. Our second rule starts at 0, but doesn't include 0. And that's okay. It's totally possible that some x value is not defined. Now, these pieces do not need to fit together nicely. They don't actually have to sit next to each other side by side. We can have gaps horizontally. They don't have to fit together vertically. We can have gaps as we go up in the y values. If they ask you the domain of a piecewise function, it's easy. It's listed right there on the right side for you. So this graph starts way to the left, it stops at 0, it starts again at 0, stops at 4 and includes 4, and then it actually comes back and it fills in what to do when x actually equals 0. And then there's a fourth and final rule to tell us what to do for numbers greater than 4. So the domain for this one is actually all real numbers. Somehow, in some way, it takes care of absolutely every single x value. The range, well, that can be a little bit more complicated. It's probably best to find the range by using a graph. If you actually graph this piecewise function, starting and stopping where you're supposed to, it's probably the easiest way to figure out the range of this piecewise function. Okay, so that's it. We're all set. I hope this one finally worked. I'll see you in class, and I'll see you online.